As rapid urban development is happening all around the world, neighborhoods with dense high rise buildings are creating the problem of limited sunlight access, especially during winter months. Thus, it is crucial to have efficient shadow computation methods to help urban planners assess and mitigate shadow impacts for sustainable city development. However, existing systems are limited to a single step shadow computation. By single step, we mean at any given time point like 4 pm or 4:30 pm, whereas accumulated shadow accounts for a time range like 10 am to 4 pm for 3 days. State of the art methods tackle this challenge using ray tracing to accumulate shadows over time, but still suffers latency issues that limit the scale and scope of analysis. Our goal here was to efficiently quantify accumulated shadows over time. Our proposed framework gains a speed up of 6 times against the state of the art. We ensure model transferability, and our framework works across cities that are not included in the training set. We also contribute a global shadow dataset with accumulated shadow information for over 100 cities and 6 continents. Our framework supports sustainable urban planning, demonstrated through case studies on sunlight access in streets and parks, and is reported in the manuscript. In this slide, I will briefly explain our framework, which is named Deep Umbra. First, we carefully picked cities for training and test sets so that they have buildings with different height distribution and also varying latitudes, as building height and latitude contributes to the shape of shadows. The framework extracts buildings height data from OpenStreetMap data repository. We convert building height data into corresponding image tiles where each pixel represents the building height at that location. We also add latitude and season information, and together these three works as the input of our model. To train our model, we required paired ground truth images. As such, we leveraged ray tracing based methods to generate ground truth data. Then we split the data into train and test sets. Afterward, we train our model using a conditional GAN architecture consisting of a generator and discriminator. Finally, we evaluate the model using test set from cities that were not part of training. As part of this work, we have made available accumulated shadow tiles for over 100 cities in 6 continents computed using our framework Deep Umbra. The completed dataset contains 1 million map tiles, totaling of 16 gigabytes. We also have made available a web-based interface in this link that can be used to browse and visualize the global shadow dataset. There is a small demo of the web interface to browse the global shadow data where 100 cities are included and for 3 different seasons, and user can also see the stats of the shadow information and browse through different cities to see how the building height data contributes to the shadow information for that particular city. Several case studies were performed with the dataset and the tool, and the case studies are reported in the manuscript.